Welcome to the Problemas Channel Season 2, Episode 24, the episode which I titled Integral Evaluation via Scope Reduction, because in this episode we will do precisely that. We will evaluate the integral shown on the blackboard behind me using the so-called scope reduction or reduce and conquer problem solving approach, and we will do that in order to avoid a direct and a traditional fight with this integral and exaggerating for demonstration purposes. And from a pedagogical standpoint, we can think that there are no such things as traditional methods in mathematics, theoretical physics, and computer science, and there are only two things: the presence of creativity and ingenuity and the absence thereof. Before we do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the channel's homepage and in the channel's trailer section, find the episode titled The Problemas Channel How-To. Watch that episode in its entirety and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E24, we're asked to evaluate a certain Riemann integral using the scope reduction or reduce and conquer problem solving approach. In particular, just to make sure that we're all on the same page and we all understand which problem we have to solve. In this problem S2E24, we're given the following Riemann integral. The boundaries of integration are: the lower boundary is c, the upper boundary is 2c. C is a strictly positive real number, and the integrand in this case looks as follows. In the numerator, we have the single copy of x. In the denominator, we have a square root of x squared plus c times x minus 2c squared, and the integration is carried out with respect to the dummy variable x. In your early and formative years as a mathematical student, it pays to hold the following view, which I slightly exaggerate for demonstration purposes and from the standpoint of a pedagogical wisdom. In mathematics, theoretical physics, and computer science, there is no such thing as a traditional method, because there are two things and two things only. There is either a presence of creativity and ingenuity or the absence of creativity and ingenuity. As such, the whole point of this problem is to avoid a direct and a traditional fight with the Riemann integral and exercise our ingenuity and creativity and evaluate the suggested integral using precisely the scope reduction or reduce and conquer problem solving approach. And this is precisely what we will do in the next segment. The indoctrinated audience on this channel already knows that there is more to mathematics than meets the eye, that mathematics is an art of telling a story of how and why. We want to know what is a beautiful and elegant story behind the process of evaluation of this here Riemann integral. And that is precisely the idea and the reason why I brought this problem to your attention, because we do not want to engage into yet another mundane and boring integral calculation problem, because God knows there are plenty of mundane and boring integration problems out there. So here we want to exercise our ingenuity and creativity and use the scope reduction problem solving approach in order to evaluate the integral over here. In case you missed it, I described the mechanics of the scope reduction problem solving approach in Season 2, Episode 21. I'll write it down for you over here, guys. Season 2, Episode 21. If you missed that episode, it may be a good idea for you to find it and watch that episode in its entirety. But in a lightning round, according to the scope reduction or reduce and conquer problem solving approach, if it is the current difficult problem that we cannot solve, then there exists a simpler and related problem that we can or cannot solve. Our job is to find that simpler and related problem and try to solve it. Let's say we cannot solve that simpler and related problem. Then recursively, for that simpler and related problem, there exists a simpler yet related problem that we can or cannot solve, and so on. By following this recursive process, we create simpler and simpler related problems until we arrive to the so-called proverbial rock bottom simplest related problem that cannot be simplified any further. And if we can solve that simplest rock bottom related problem, and if we can gain certain tactical and strategical insights into what is going on with this type of problems, then we may carefully and slowly climb out of the hole, so to speak, and solve the next slightly more difficult problem, the next slightly more difficult problem, and the next and the next and the next, all the way to the original problem, which we hopefully will be able to solve, because in all this optimistic, pessimistic journey, we gain certain insights, and with all these cumulative and aggregate insights, we can attack the original problem. So here we take this problem over here to be the original difficult to solve problem. How can we simplify this problem but preserve the technical essence of this problem? Well, here's one thing we can do. Let me erase this constraint over here. We all know now that this constraint is on the books. Let me write it down over here. C is a strictly positive real number. So here's my idea. Introduce our favorite single variable real-to-real function f of x equal to square root of x squared plus cx minus 2c squared. In other words, this function is basically what we have here in the denominator of the integrand. Now let's make it a small and fun exercise. Let's say you now saw this, put your video on pause and try to think what would the next maneuver be. And again, the act of generating this idea is the act of doing mathematics with a capital M. This is, so to speak, real mathematics, generating ideas, because mathematics, amongst other things, is a play of thought. So this is our thought. This is what we decided to do over here. What is the next step? Well, if we were to plot the graph of this function, I'll draw it over here on a traditional Cartesian plane, x, y, then graphically this function will be represented with two strictly positive branches, because this is plus square root, and these points over here will obviously depend on the specific value of c. So this function is defined on the appropriate intervals, we understand, but c is strictly greater than 0, so we'll take the right branch. But this is just details for those who want to investigate this further. And consequently, what is the next maneuver that we will carry out? Well, let us see what will happen if we compute the first derivative of the function f of x. In other words, we take the first derivatives of both sides of the equal sign with respect to x. What will happen? On the left-hand side, we will have f prime with respect to x of the function f of x equal to the first derivative of the square root of something is always what? 1 over 2 square roots of something. But because this function is composite, we also multiply this 1 over 2 square roots of something by what? By the first derivative of whatever sits under the square root. So in this case, we'll have two terms. The first derivative of a constant 0 vanishes. The first derivative of c times x is what? C. And the first derivative of x squared is what? 2x. 2x in this case will cancel out. 2 in the numerator will cancel out with the 2 in the denominator for the first term. For the second one, it will not. And we split the summands in the numerator of this first derivative into two separate expressions. In the first one, we will have x over square root of x squared plus cx minus c 2c squared. That much we understand, because again, 2 in the numerator canceled out with the 2 in the denominator, precisely thanks to the presence of the square. And in the second term, what will we have? We will have c over 2 square roots of x squared plus cx minus 2c squared. That much we also understand. Here 2 does not cancel because x is in the first power, c over 2. And what is the next maneuver? Well, the next maneuver is this. We multiply this through by dx, dx. And what is the next maneuver? Precisely, we integrate all this mass from c to 2c, integral from c to 2c, integral from c to 2c. Now, what do we have in this manipulation as a result of this manipulation? On the left-hand side, we have what? We have a classical representation of the so-called second fundamental theorem of calculus. Integral of a derivative is the function itself. So on the left-hand side, we have f of x evaluated between 2c and c. Then what do we have here? What is this guy? Well, this, let's designate this with I. This is our integral. This is I. And what do we have here? Here we have plus c over 2 is a multiplicative constant by the property of definite and indefinite integrals. For that matter, we factor it out. So here we have from c to 2c, here dx over square root of x squared plus cx minus 2c squared. That much we understand. Everyone should be on the same page at this point. And what is this? Well, this is trivial. This is zero work. Let us do this together. The value of the function f evaluated at the point x equals 2c is what? 2c squared is 4c squared. 4c squared minus 2c squared is 2c squared. c times 2c is 2c squared. 2c squared plus 2c squared, 4c squared. Square root of 4c squared is absolute value of 2c, but c is strictly positive, so we drop the absolute signs. 2c. And what is the value of the function f evaluated at the point x equals c? Well, let's see. C squared plus c squared. 2c squared minus 2c squared. 0, square root of 0 is 0. So we have here big fat 0. As such, on the left-hand side of the equal sign here, we have 2c. And now let me write it down over here, guys. I will be erasing, again, this board frequently, but we will keep track of all this work together. So what do we have here? We will have, just to keep track, 2c equals to I plus c over 2, integral from c to 2c dx square root of x squared plus cx minus 2c squared. I simply wrote down this result shown over here, neatly over here. And what do we have now? Well, now we have a trivial linear equation in I. And I, our integral sought after, is equal to 2c minus c over 2, definite integral from c to 2c dx over square root of x squared plus cx minus 2c squared. I hope that you all guys can see this result over here. Now, what does this result constitute over here? Tell me, guys, what is going on over here? Well, this result over here constitutes precisely the reduction of the original difficult to solve problem to actually a previously solved problem, because this over here, the integral shown on the right hand side of the equal sign, is a typical table integral. And pretending for demonstration purposes, let's say you are a research mathematician or you are a theoretical physicist who is chasing her or his Nobel Prize. So what will you do? You will never futz with this kind of integrals by yourself by hand. You will simply go to the table of integrals, pull out the value, for example, for the indefinite integral shown over here, apply the boundaries of integration and move on. Problem solved in 2 minutes or less. Game over. All courtesy of the power of the scope reduction or reduce and conquer problem solving approach. And if you know what the value of this integral is already, or you know how to evaluate it, then you can skip to the end of this episode. But for the benefit of everyone on our channel, I will show in detail how to evaluate this specific integral. And there is a pedagogical point to be observed over here also. We will see how much work is saved if we already reduce a given problem to a previously solved problem. As promised, in this and couple of next segments, we will show the evaluation of the table integral shown over here. And again, it is a good idea for each and every younger student of mathematics to do one or two or several fundamental problems in each vaguely defined layer of mathematics, precisely in order to see how much work is being saved by these previously solved problems, and in order to begin comprehending the true awesome power of the scope reduction problem solving approach, and to appreciate exactly the success of us being able to take a difficult to solve problem and reduce it to a previously solved one. Here we will take this integral on head-on in this case, and we will do what we will for now designate with J. Let me do it over here as the indefinite integral. We'll fight with this guy right here. And this fight is actually was fought by the people who came before us, namely by Leonhard Euler, the Swiss-born mathematician. And if Euler was here, you can rest assured that Euler's mathematical nose was right on the money. So what do we do first? Well, let's see. Here we will observe the following. We will basically complete the square on the expression shown under the square root in the denominator of this here integral, and that is trivial and straightforward to do. We represent c times x as 2 times x times c over 2. So c over 2 is our term. We add it to this expression, and to balance it out, we subtract it. So 2c squared minus c squared over 4 will be what? Will be minus 9c squared over 4. And once we carry the 4 out, we will have the following. X squared plus cx minus 2c squared will be precisely 1/4. I'll use the square parenthesis just as a syntactic sugar. 2x plus c squared minus 9c squared, like so. Again, we showed how the completion of square works over here. There is no high-flying signs over here. This is a typical middle school step. We all should be able to carry this out. And here again, just to deal with whole numbers, so to speak, to avoid fractions, we factor 1/4 out. Now, when we take the square root of all this mess and flip it into the denominator, what will we have? We will have two integrals dx over what? Over square root of 2x plus c squared minus 9c squared. This will be a square root. And what will we do over here? What is the next maneuver? The next maneuver is quite straightforward. We simply collapse 2x plus c into a new variable. We'll call it, let's say, t equals 2x plus c. It is trivial to see that dx will be dt over 2. 2 in the denominator and 2 in the numerator cancel each other out. And what do we have in the end? The integral of dt over square root of t squared minus 9c squared. And this is precisely the table integral to which I was referring. So in case you are a research mathematician or a theoretical physicist who is chasing her or his Nobel surprised, then you will never deal with these integrals by hand yourself. You will look them up and move on. Problem solved in 2 minutes, all courtesy of the awesome power of the scope reduction problem solving approach. But in order to see how much work is being saved and thus comprehend the awesome power of the scope reduction and reduce and conquer problem solving approach, we will unroll all this work by hand. So what is a technically useful substitution over here? To the best of my knowledge, this is a substitution that was suggested by Leonhard Euler again. And sometimes the modern students of mathematics, especially the younger one, like to fly through these things. But like I said before, it pays to at least once or twice or several times initially work through all these situations by hand first and see how that works. So what is a favorable substitution over here? A technically useful substitution over here is the following. T equals to, what is it? 3c times e to the power plus w plus e to the power negative w over 2, and the new integration variable will be w. What does that mean for us? What is the first differential of dt in this case? Let's write it down together. This is again a trivial task. dt is 3c e to the power of w minus e to the power negative w over 2. Would you agree that this is the case? Yes, this is straightforward. The first derivative of the exponential function with a positive exponent is itself, the function itself. Here we multiply the first derivative of the exponent, carry minus over here, and we get dw. Next, let us compute t squared. What is t squared? From here it follows that t squared is what? Will be 9c squared e to the power 2w plus 2 plus e to the power negative 2w over 4. This is again nothing beyond middle school curriculum. We simply squared both sides of the numerator and the denominator, both sides of this fraction, according to the a plus b squared. And now we want to calculate. From here it follows that t squared minus 9c squared will be what? Let's write it down. 9c squared is a common factor here and here. We carry it out. So here there will be big parentheses, and what we will have in it? E to the power 2w plus 2 plus e to the power minus 2w minus 1, 4. So bringing all this mess over here to the common denominator, we will have minus 4 over 4. Now, what do we see? What is the magic over here? Plus 2 minus 4 will be negative 2, and e to the power 2w minus 2 plus e to the power minus ew is what? Is a perfect square. Exactly. Let's write it down here. It is equal to, let's write it down over here, 9c squared of what? E to the power w minus e to the power minus w over 2, exactly, squared. You see how beautiful these things fall out? Exactly. Now, when we take the square root of this beast right here, we will get what? Again, absolute value, but we take the positive version of this, 3c, and here we remove the square sign, we get this expression over here. But for the power, for the dt, for the differential, we get 3c and this mess in the numerator. What does that mean? That means that our integral, let me do this little stunt over here so you guys can follow. I'll put it over here, big mess, but this is what it is, the integral over here. Make sure that you guys follow. Via this substitution over here comes down to, let me just maybe delineated like this, comes down to what? Comes down to integral of dw. Exactly. This is a trivial integral by itself. So here we have w plus a constant of integration. And I'll take a little bit of time to erase the board and prepare it for you for the next computation. But here, essentially, we are done. We just have to unwind the series of substitutions, w into t and t into x, all via this and via this, apply the boundaries of integration, and we are pretty much done. Now that I made more room on the board behind me, I simply rewrote our indefinite integral j that's taken from here verbatim without the bounds of integration. We deduced that the value of this integral is w plus a constant. W is shown over here, t is shown over here, x is t, t is w, so x is w in some sense. And now we just have to bring it home and unwind the substitutions. Some members of our audience will say, Roman, why are you using the sum of exponents and you're not using explicitly the hyperbolic cosine, which is what it is? Well, I'll answer that question with another question. When it is and why sometimes it is advantageous to look at the hyperbolic cosine and sine as a sum of the corresponding exponents. Well, sometimes it is advantageous to look at the hyperbolic cosine and sine as a sum of exponents when, for example, we want to construct the Fourier series of these functions, hyperbolic cosine and hyperbolic sine, on certain interval. Constructing the Fourier series of the exponential function alone, taken in isolation, like so, for example, is a straightforward task. And once we know the Fourier series of the exponential function over a certain interval and over sines or cosines, for example, then we know this guy over here, the Fourier representation of this exponent, sum the two and divide by 2 for the hyperbolic cosine, and boom, voila, we know the Fourier series of the hyperbolic cosine. Likewise, subtract one from the other, divide, we have the Fourier series of the hyperbolic sine. But anyway, the deal here is the following. Yes, it is a hyperbolic cosine, and graphically, let us depict it maybe over here if we have enough room. This is our proverbial x-axis, this is y-axis. Graphically, the partial graph of the hyperbolic cosine shown over here, modulo the multiplicative constant, let's ignore it for now. Fundamentally, the graph of the hyperbolic cosine can be represented as two branches that are positioned very specifically. One branch runs like so. Let's say this is 1, and the other branch runs like so. This is the hyperbolic cosine. These branches are symmetrical, and by looking at the graphical representation of our function, it is sometimes quite straightforward to predict the quality of the inverse function, because here this is what we have to do. We have to find the inverse of the function where we need to represent w as a function of t. And how this prediction can unfold? Well, if we can construct several straight lines parallel to the x-axis, and here we can do that, for example, like so. Here, if these parallel straight lines intersect the graph of our original function in more than one place, and we know that the inverse function will constitute more than one branch. In this case, it will have two branches, and we can even make a fearless prediction of how these branches will look like, because in order to graphically represent the inverse of a given function, we reflect the original function in the y equals x straight line. We'll do that in a moment, but how do we unwind the representation of w in terms of t? Well, usually you will do it in your mind. For those who cannot do it in their mind yet, we will make a substitution, and here we'll make the following maneuver. We'll write e to the power of w equals z temporarily, just for those who cannot handle these things on the fly in their mind, so that later on you can handle it on the fly and in your mind. What will we have then? We will have then t is equal to 3c over 2 of z plus 1 over z. We have a plus, right? So this is what we have with the substitution. Then that means what? 2t over 3c is equal to z plus 1 over z. And what does that mean? In that case, if we multiply this equation through by one copy of z, what will we have? Z squared minus 2t over 3c z minus, we carry this term on the right hand side of the equal sign, 1 over z times z plus 1 is equal to 0. This is our favorite polynomial equation of degree 2. Here is the degree 2, so we write down its roots right away. z12 is equal to t over 3c plus minus, you understand where this came from, minus b. This is our proverbial b coefficient. This guy right here is b. I do not want to throw too many symbols at you guys, but you understand what's going on. So minus b over 2 becomes t over 3c plus minus square root of, let's compute this together, b squared will be 4t squared over 9c squared minus 4 times 1 times 1. Once we bring everything under one and the same denominator, carry 4 out, square root of 4 is 2, over 2a cancels out, and what do we have left in the under the square root sign over here? We will have t squared minus 9c squared over 3c. That is our answer. And now we do the reverse substitution. Instead of z, we write down what? We write down e to the power of w. And once we logarithmicize both sides of this expression, the natural logarithm of e to the power of w will be what? Will be w. It will be w equals logarithm of what? T plus minus square root of t squared minus 9c squared minus the logarithm of 3c, and we'll see in a moment why I moved out the 3c from the expression in the logarithm over here. Why did I do it? Precisely, I did it because this term right here will be absorbed by the constant of integration. We do not care about it. This goes into the plus a constant land, and essentially the median substantial answer in this case is this. And what do we have here? Precisely, we will have the two signs, plus and minus. This will correspond to two branches of our inverse function. One branch reflected in the x-axis will run which way? Well, it will run apparently this way. Reflected in the, it will run this way. Let's see, this way, this way. So it will run this way. And the other branch, this guy, will run this way. So here I'll write it down for you guys over here. This will be the logarithm of t plus square root of t squared minus 9c squared. So far so good. Natural logarithm in base e of t plus square root of t squared minus c squared. And the negative branch will be what? The negative branch will correspond to the minus sign. So here at the bottom, how should I make sure that you guys see it? Well, let me try it here. Logarithm of t minus square root, I'll eat x, of t squared minus 9c squared like so. Now, between these two branches, which one do we pick for our calculations? Apparently, because x is positive here, c is positive, 2c is positive, so x must be strictly positive. Here we argue t must be positive, w we think must be positive, so we take the positive branch and we write down our answer over here. Let me squeeze it. Let me do a little bit of carving over here. So what do we have over here? Let's write it down. The logarithm of t, we will take the plus sign, t squared minus 9c squared plus a certain constant, which in our case we do not care about because we're about to apply the limits, boundaries of integration in the next moment. But let me, now that we understand everything, I will erase the board a little bit, and maybe let's do again, before we jump to the final calculation, instead of t, we substitute 2x according to this. So far, we're all on the same page. T here becomes t shown here. So our integral j, let me write it down over here for you guys. The integral j is equal to the logarithm of 2x plus c plus square root. We'll take, it looks like the entire board, logarithm of 2x plus c of what? 2x plus c squared minus 9c squared. So now we have plus a constant of integration, of which we do not care about. Here, pedantically, we need to say when and where this formula applies for specific interval, which is legal for this function over here. But because we will be doing our applying boundary of integration, for now we will skip. And again, I will take a small break, erase the board, and prepare it for the final computation shown over here. In order to make sure that we're all on the same page, during the short break, I took the liberty to erase the board and prepare it for the final step. Here we obtain the integral, the value for the integral j, which is basically our integral shown over here without the boundaries of integration. This is the answer with the w and t substitutions carried out, reverse substitutions carried out. So that means that the value of this integral, I rewrote it over here, is our integral j evaluated between the boundaries of 2c and c. Here I simply wrote down the expression shown over here so that we all see what is going on. And as the final step, we need to evaluate this expression at two endpoints, 2c and c. Let us do that together. On the top, we'll carry out the computation associated with 2c. On the bottom, we'll carry out the computation associated with c. So when x is equals to c, x is 2c, 2 times 2c is 4c, 4c plus c is 5c. So let's write it down so that we do not forget 5c. 5c squared, 25c squared, 25 minus 9 is 16, square root of 16 is 4. We take the absolute value of c again because c is strictly greater than 0. So 5c plus 4c comes out to what? Exactly, comes down to the logarithm of 9c minus. Here on the bottom, we'll do our work associated with the lower boundary of c. When x is equals to c, here we have 2 times c is c, 2c plus c is 3c. And what do we have here? 3c squared becomes 9c squared. 9c squared minus 9c squared, 0. Square root of 0 is 0. 0 plus 3c is 3c. So we have minus logarithm of 3c. And now, lastly, we use one of the fundamental properties of the natural logarithm. We write it down as follows. This is the logarithm of 9c over 3c. C and C cancel out. 9 factors as 3 times 3. 3 and 3 cancel out in the numerator and denominator. And we have a very neat answer, log of 3. So our integral shown over here is simply the natural logarithm of 3. So here we write down our answer, 2c minus c over 2 times logarithm of 3. And let us be polite over here and write down the answer to the original problem. So the integral from c to 2c of x over square root of x squared plus cx minus 2c squared dx is equal to, here we'll say under the constraint that c is a strictly positive real number, is what? 2c minus c over 2 times the logarithm of 3. And here, let me box it in for you guys. This is the answer. And in some sense, again, early on in mathematics, nobody really cares about the final answer that we see over here. But we care on this channel, we care a lot about how that answer was produced. And again, one more time, we produced that answer by using specifically the scope reduction or reduce and conquer problem solving approach. We introduced a single variable real-to-real function, which looked like f of x is equal to square root of x squared plus c times x minus 2c squared. That was our move where we tried to think like a mathematician. We took the first derivative, we integrated all these results through, reduced the difficult to solve problem to a simpler integral, and we already showed for demonstration purposes how much work is being saved when we reduce the current difficult to solve problem to a previously solved problem. This is the answer. This is how these answers are obtained, and we thus produce the answer. And again, in theory, if you will not be carrying out all these computations by hand, then you will solve this original, let's say, pretend difficult to solve problem in the span of about 2 minutes or so. This is it for the mathematical problem S2M26, and we will move to a new challenge next. With this episode, we conclude our dedicated study of the scope reduction or reduce and conquer problem solving approach. But that does not mean that we should forget all about it. Quite on the contrary, the moment we learn about a new problem solving approach, we should incorporate that new problem solving approach into our problem solving journeys right away and rely on our creative juices to figure out when to use it and how to use it, splice it here, splice it there. And amazingly enough, little by little, we already have something to write home about, because at this point we know how the following problem solving approaches work: transform and conquer, reinterpret and conquer, reverse order or reverse and conquer, if you will, the space-time problem solving approach, the equation problem solving approach, and now the scope reduction problem solving approach. Starting with the next episode, we will take on our initial dedicated study of the so-called scope expansion problem-solving approach, and we will learn that, amazingly enough, sometimes instead of reducing the amount of material that we have to deal with, on the contrary, expanding the amount of material that we have to deal with, sometimes it helps us to solve this or that mathematical problem, and that is exactly what we will do in our new challenge, the mathematical problem S2M27. And in that problem, we are to show that it is impossible to locate the center of a given circle using the Euclidean straight edge alone. And maybe you know about it, maybe you do not, but the impossibility proofs in mathematics are usually quite challenging to put together, and that is precisely we will take this problem on. And the technical essence of this problem is the following. Let's say the mathematical oracle walks into this room where I make this episode, and the oracle tells me, Roman, get out of the room, close the door, I walk out of the room, close the door. The mathematical oracle draws a perfect circle on a model of the Euclidean plane. Then the oracle tells Roman, come in. I walk in, and the challenge is this. Roman, here is the model of the Euclidean straight edge, which is basically a rule with no markings. And the challenge is to take this here circle, and in a finite number of steps, each of which is deterministic, and the description of the finite number of steps must be finite itself, just to make sure. Construct an algorithm according to which the center of such a circle will be located if you do not know where that center is. Of course, the mathematical oracle is prodding us to generate a correct and valid proof that it is impossible to do, and that is exactly what the essence of this challenge is. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2E24.